Okay, so last we left off, I believe that we were talking about the conventional equation. Is that correct? Or am I making stuff up? Okay, well, we're talking about a conventional equation, right? So the conventional equation is just how we would normally write the chemical equation. We normally balance it and everything like that, right? But we know that these are aqueous. Since they're aqueous, basically means that they're able to be dissolved. Since they're able to be dissolved, they can be broken up into their ionic forms. So in the case of lead 2 nitrate, we know it's lead 2, so it's Pb 2 plus. And it's aqueous. Plus 2 3 minus. So since there's 2 of these, and it's the lead that's holding them together, right? As soon as we let loose with the lead, they're like independent. So that's why this becomes a coefficient in front. Plus 2 sodium ions. Plus 2 Cl minus ions. Now on the product side, if anything is a solid, liquid, or a gas, we don't separate it. It stays together. So since this guy is a precipitant, it's going to be a solid. So we're going to keep it together. But since this guy is aqueous, it's going to split up. So the easiest way to remember this, and I think I said this the last time, water is going to be a homewrecker. It's going to break up anything that's aqueous. So since it's aqueous, it's in water, it's going to be able to be broken up into its ionic form. Okay. Are you guys with me? Any questions?
Yes.
Yes, a question, or you're with me?
I have a question, Dr. Henry. Okay. It's in line with what we are looking at, but it's still from the exam, right?
Say one more time, please.
I'm saying I have a question. It's in line with what we are doing, but it's from the exam as well. I'm wondering when, like in this, not in this case, in the case where the ions actually, there's no solid formed, right?
Yeah.
And then we add a different substance, like what we did in the exam, right?
Mm-hmm. Like number 8.
Number
right?
8, yes. Yeah. But what we added, you said cobalt would displace the ions.
That's right.
But in that case, Fe is higher in the reactivity series.
Yeah, but in this case, it doesn't matter that it's Fe. It's not Fe solid, it's an Fe ion.
Okay.
So this means it's already in solution. It's already dissolved. Right? When it's a metal, when it's a solid, and it doesn't have a charge, right? That means that it's able to replace things. Does that make sense?
Okay, so the NO3 would still react with cobalt? Is it the NO3 or? Okay, something will react with cobalt to make it a precipitate, right?
That is correct, yes. And we'll talk about that today.
Despite the reactivity series?
Yes, despite the reactivity series. The reactivity series only works in the case of single replacement reactions. So if you're doing a double replacement reaction, it's not gonna work. It doesn't work.
Okay. Thank you.
You're welcome. Good question. I like it when you guys start thinking, you know. Okay, so you guys all see that, right? Everybody sees where I'm at. You're good with this? We're all good. Okay, so the next part is, so have you guys ever been to a party? Anybody been to a party? I know the brothers from that. That's from that. You guys go to parties, right?
I used to, I don't anymore.
Oh, okay. That's what she tells us, right? She's like, I used to. Yeah. What about the other Brenda? Do you still turn up?
No, used to too, ever since I had my baby.
Oh, okay. The baby slows you down a little bit. I can attest to that one there. So, okay. So, but when you guys went to a party, have you guys seen those people that come with somebody and that one person just sits on the wall, don't even think about it, and the other person is just mingling with the social butterfly?
Your sound keeps going on and off.
It keeps going on and off.
Yeah, so we didn't hear what you said.
Okay, let me see if I can make some adjustments here.
Okay.
How about now?
It has an echo to it.
Okay, give me 1 second. How about now?
It's good.
It's good?
Mm-hmm.
Okay. So we're bypassing the room, so we'll be talking through my computer. That means I can't run away from it or anything. Okay, so as I was saying, if you go to a party, there's always that somebody brings somebody to the party, right? And then they just stand on the wall. They don't interact with anybody. The other person is the one that interacts, and they end up hooking up with somebody else, or chatting with somebody else. Okay, so the way you look at that person is they're a spectator. They just come there to watch other people have a good time. They're not going to have a good time. They're not going to do anything to have a good time, right? And so those spectators, I need to fix this. Those spectators are not going to be remembered by anybody, right? So you're kind of like getting rid of them, okay? So in the case of this is called the total ionic reaction here. Total ionic reaction that we just wrote in green. We're going to identify the spectators. Now, a spectator they look exactly the same on both sides of the chemical equation. Now, if they're with something, they're not exactly the same, okay? So can you guys help me identify the spectators?
Sodium.
Okay, so we have sodium.
And NO3 ion.
So we have sodium and you said NO3 ion. Okay, so those are going to be our spectators. Okay, so sodium and the nitrate ion. Okay, now they're spectators. Their job was to only bring that other person to the party, right? So in this case, nitrate brought lead-2 to the party, and sodium brought chloride to the party, and lead-2 and chloride hooked up at the end of the party. So lead-2 and chloride are going to hook up, so they're going to be the net ionic equation. Okay, so the lead ion, lead-2 ion, and the chloride ion are going to be what's going to be left after we get rid of the spectators. And it's going to form lead-2 chloride. Okay, questions? And Alexis, I'm not ignoring your question. I just wanted to finish this thought before I addressed your question. Okay, do you guys see that? Yes, no, maybe?
Yes.
Okay, good. Okay, Alexis, what is your question?
I was trying to turn in the peer review, but you have it to text only, and it doesn't allow us to submit the picture. I don't know.
Okay, so I'll adjust that. Thank you.
That's it.
Let me do that real quick. Okay.
Oh, actually, regarding that sheet,
Yep.
on the right side, is that for you to fill out as you?
Yeah, it's for me to fill out. That's not for you
Okay.
guys. Yeah.
Okay, I figured so. Thank you.
Yeah, that's what I'm going to be using to grade you guys. So
For the peer review, do we just give them the letter or
just a letter grade.
oh, okay.
Yeah, no points, because then I decide that scale there. So
Okay.
And do we submit it individually?
yes, that one is going to be submitted individually. Don't submit it as a group. Yes, you don't have to share that with anybody. That's your personal thing, you know. So
Okay.
okay.
So technically we're grading our classmates, right? The people that we work with. So
That's right.
Okay.
You're grading the people that you work with, not other people. Yeah.
Okay.
Yeah, just the people that you're working.
One more question. In terms of turning stuff in, aside from turning it as a group, do you want us to turn in like our report that we did individually?
What do you mean by the report that you did individually? I'm not going to read anything individually for your group project.
But do you want us to specify what section pertains to us, like what work we did?
Nope, because that
Okay.
isn't going to make a factor because it's a group grade, right?
Gotcha.
So at the end of the day, I am concerned about the finished product. I don't care if Johnny did 1 page or if Johnny did 20 pages, right? Long as that finished project is done, right?
Okay.
It's kind of like a job. Do your boss really care who does the job? Long as the job gets done and done correctly, I should say.
So that's where the peer review comes in, right?
Exactly.
Okay.
Yes. So that's why the peer review becomes important, because you guys, you know what you did and you know what Johnny did, right?
Mm-hmm.
Sorry, my computer is running really, really slow. Any other questions? So I have a question for you. How many of you guys were happy with the product that you guys made? And actually, I'm going to ask you not to turn them in until after your presentation, because I want to give you guys a chance to, not change your grade, change what you graded somebody, just in case somebody don't show.
Oh, okay.
Okay. So
and you
I
want-
just adjusted.
Okay.
Yeah. Me and
And
Edgar were
you-
talking about that earlier anyway. So I thought I did it earlier, but it didn't say. Tell me if it shows now.
Oh, okay. Let me check. And you want it digitally submitted, right?
Yeah.
So what was the question that you asked before this?
I said, how many of you guys actually enjoyed the group project?
No.
Wow.
I enjoyed the video part of it.
That's what I was gonna say. Our group had fun recording the music video.
Mhm.
Good.
Yeah, I had a good time. It took a while to get everybody on the same page, but I think I steered them in the right direction.
Good. Good. Okay.
Yeah, I see different file types are accepted now, and the date has been changed to the 14th.
Okay. So it did save this time.
Yeah.
Yeah. It's horrible when I try to do it in the on the computer. I mean on the on the phone. So because I try to do it as soon as somebody talks to me about it, because otherwise I forget. I get distracted and I forget. I'm like, how many of you guys seen that movie Up?
I have.
You have? Yeah. I'm like one of the dogs, squirrel, so. Okay. So we've talked about the total ionic equation. We've talked about spectators, right? So you feeling comfortable with this yet? Okay, that's all right. We're going to do a couple practices anyway, so. Okay. So now this is going to be the case when we're working also with strong acids. Strong acids are going to totally solubilize, okay? Strong bases are also going to totally solubilize, meaning that they're going to break up into the ionic parts, okay? We've already talked about that. You guys should be comfortable with it already, okay? Now weak bases aren't going to do that, okay? So even though that their state is considered to be aqueous, they're still going to try to stay together, okay? Weak bases are going to do that, okay? So speaking of that, can you guys tell me what is a weak base? Give me an example of a weak base. Anyone? Anyone? Man, I can hear a pin drop.
Are they
Okay,
made from non-metals?
what was that?
Are the weak bases made from non-metals?
So yeah, a weak base could be something that's made from a non-metal. So often a weak base isn't soluble. So if you have group 2 metals with, let's say, hydroxide, a lot of times those are going to be weak bases. I believe barium hydroxide, unless there's water added to it, is going to be a weak base. I mean, as in water attached to it physically, because it's still going to stay together. Okay. What about a weak acid? There's one that you definitely. Ammonia is a weak base. That is correct. Ammonia is a weak base. Yeah. What about a weak acid? Now, if ammonia is a weak base, what would be the acidic form of ammonia? By the way, is the audio better still?
Yes.
Okay, so let's talk about weak acid and weak bases. So we know that any carbon acid, such as acetic acid, citric acid, lauric acid, anything that has carbon in it is going to be a weak acid. Okay. Also, anything that ends with OUS acid. Okay, so that's chlorous acid. That is sulfurous acid. That is nitrous acid. Okay, all of those are going to be weak acids. And then we know that hydrofluoric acid is going to be a weak acid. Although all of the other ones, hydrochloric acid, hydroiodonic acid, hydrobromic acid, all of those are going to be strong acids. Do you guys remember why hydrofluoric acid is the only exception? Okay. No one? No one want to take a guess?
Would you ask hydrofluoric HF?
Yes. So why is hydrofluoric acid is the only exception where hydrochloric acid, hydroiodonic acid, hydrobromic acid are all strong acids?
I'm sorry, you're asking why is it the case that it's a weak acid or why is it strong acid?
Why is it that hydrofluoric acid, HF, is a weak acid? HF is a weak acid.
Because the higher you go on the table, the weaker it is?
Nope.
No. I know like hydrogen likes to stick, right? If it's H plus.
Yeah. So, but HI is a strong acid.
Hmm.
Well, okay, sort of what you're saying is true, but why?
Is it because of the ionization energy?
Is it the ionization energy?
It's the electromagnetivity of fluoride.
The electronegativity, yes.
Yes,
So we know
sorry.
that electronegativity of fluoride. Fluoride is a
It's the
very
greatest.
strong electronegativity, right? It also means that it's also a very much a bully, right? It doesn't want to let anything go, right? Because it's so small, it's kind of like Napoleon. You know, Napoleon was thought of being very short, but very much a dictator, right? So in the chemistry world, fluoride is like Napoleon. It's the smallest, one of the smallest elements, but it also has the strongest pull. It's very strong, okay? And because it's very strong, it's not gonna let loose that hydrogen. It's gonna keep it right next to it. Have you guys ever met anybody who's been in an abusive relationship? Somebody who's very clingy and very, you know, clingy and dictatorial. You know, it's like, no, you're not going to the bathroom without me. No, you can't go with your friends out. None of you guys have met anybody like that or been in a situation like that. Me and my cat. Okay. So your cat won't let you go. She's very clingy. Okay. So that would be a good example, right? So in that case, they want you right next to them all the time when they want you there, right? And so fluoride is going to be exactly the same way with the hydrogen. It's when it keeps it there. So it's not going to want to dissociate. Where all of the other ones, hydroiodonic, hydrochloric, hydrobromic, all of those guys, they're going to want to dissociate as soon as they hit that water. They're like, oh, see ya, bye, boo, you know, go do you, you know. So they're going to ionize. So they're going to go directly to the ionic forms. So that one's going to be H plus Br minus. and of course, aqueous. Where hydrofluoric, most of it is going to be in this form, and only a little bit of it is going to ionize. And so this guy is going to be able to go both ways, but it's going to favor them being together. Okay. So that's just a quick reminder. Okay. Okay, so let's go ahead and try this problem up here. It says, when a strip of magnesium metal is placed in iron 3 chloride solution, a magnesium chloride solution results, and solid iron also forms. Develop the net ionic equation for the reaction. Okay, what are my reactants? Mg,
Magnesium chloride? Sorry,
now somebody told me that it's magnesium metal, okay? And now my reactants, not my products, and
Iron
iron
3.
3, yeah.
chloride, yeah.
Okay, what is the state of the iron 3 chloride? Solid, liquid, gas, or aqueous? That's right, aqueous. Okay, what type of reaction is this, by the way?
Single displacement?
Single displacement, okay? So then what should be my products?
Magnesium chloride?
Okay, chemical formula for magnesium chloride?
Cl2?
Solid, liquid, gas, or aqueous?
AQ?
And there's my other product.
Fe?
Solid, liquid, gas, or aqueous?
Solid?
Okay, good job, Stephanie and Brenda. Is it balanced? No, you're right. Okay, what do I need to do to balance it? Three in front of the magnesium. Okay. A 3 in front of the magnesium chloride. Okay.
And a 2 in front of iron 2 chloride.
Okay. Okay, everybody agree? Okay, so this being our conventional equation. Okay. So then our total ionic equation that's going to be okay. So here, are we going to do anything with the magnesium? The magnesium solid? No, that's right. So we're just going to bring it down the way it is. Okay. What about the iron 3 chloride? Aqueous.
Fe3 plus.
Okay. So we're going to have 2 Fe3 plus. Okay. And that's right,
6Cl.
6. That's right, 6 chloride ions. That's right. Okay, on the other side,
Three Mg.
is it just 3 Mg?
3Mg2 plus,
Okay.
the ion.
3 Mg2 plus. That's going to be aqueous.
And 6Cl.
And
Fe.
we're just going to bring that down the way it is. Fe, 2 Fe solid. Okay, so that would be our total ionic equation. So who are our spectators?
Chlorine. Chloride ion, sorry.
You said the chloride ion, okay? So our net ionic equation is going to be Mg solid plus 2 Fe 3 plus AQ and that's going to yield 3 Mg 2 plus plus two Fe solid. Okay, so now I have a question for you. Can I hold you? Can I put you guys on hold for 1 second? But I'm going to ask you this question. I want you to think about it. Why is it that the Mg and the Fe's don't cancel each other out on both sides? Think about it, and I'll come right back to you. Okay. You guys want to hear some good news?
Yep.
So I just got off the phone with the old, well, he was the old dean here at this college, Mr. Pimentel. He's now the president at Fresno City, and he just called me up about position. So yeah, so it's pretty good. He got a call about me about a position. So
Congratulations.
yeah,
Congrats.
yeah. So then it's going to be the hard decision next. You know,
Which
so
one
but
do you
it
choose?
feels good. It feels good to be wanted. You know.
Mhm.
Okay, so let's go ahead and finish. So do you guys need to answer my question? So, why? Why don't we cancel these guys out? Are they
Because they're
exactly
different.
the same?
No, they're different. There was a change in aqueous to solid in the Mg, and vice versa
Okay.
in the Fe.
Okay, cool. What was that? Let's see. Somebody said, let's go. I am not gonna quit. No, no, no. We're gonna finish this. Don't get happy there, Angel. No. And all you guys should pass, but you're gonna earn it. You're not gonna get it because I'm out. I'm not out yet. We're not done. So
It means you're doing
I
a
haven't made
good job.
decision. I haven't made a decision on anything. So what was that?
It means you're doing a good job, a great job.
Yeah. Okay. So you're right. That is exactly right, because we noticed that there's going to be changes. And also somebody said because of the ions. That's exactly it. That's great. That's great. Okay, so let's move forward. Feeling good. How are you guys feeling? Can you guys handle some more? Okay. So single replacement, oxidation, reduction, reactions. Okay. So redox is what we call it. Now, if we go back to that equation, I'm going to go right back to the one that we just did. I'm going to write it up there, but just the net ionic one. Okay. So you guys can see it. It'll be more clear there. So we had I got too happy that I erased things before I finished. And I know it's in different order than it was. The order doesn't necessarily matter. What matters is what's happening. Okay, I'm going to talk to you guys real quick about this. Okay, so there's this notion, what we call oxidation state. Now, oxidation state basically means it's the state, and we're paying attention to electrons, okay? So every element, its oxidation state, when it's an element, when it's a solid and there's no charge associated with it, it has a 0 oxidation state, okay? I'm gonna write that on the top of it in a different color. So this here, stop. Okay, so magnesium, since it's an element, it's going to have a 0 oxidation state. Over here on the product side, since we have iron and there's no charge associated with it, it's also going to have a 0 oxidation state. Now, the oxidation state of the ion is going to be, it's going to let me get away with not having it balanced. The oxidation state of the ion is going to be the charge on the ion. So in the case of this iron, its oxidation state, each of the iron is going to have a 3+. So, right, +3 oxidation state. And then over here, this guy's going to have a +2 oxidation state. Now, the oxidation state just keeps track of the number of electrons that are going to be passed, right? So I'm going to write this down so you guys can remember, type it out for you. And at the level that you guys are at, we're not going to get too deep into it, but we're going to talk about loss of electrons. Okay, so if I'm going from a 0 oxidation state to a +2 oxidation state, that basically means that I've lost electrons, right? Because it's +2. Okay, so magnesium is going from a 0 state to a +2 state when it forms its ion. Okay, so when that happens, that's going to be oxidation. And then when I gain electrons, that's going to be reduction. Okay, so in the case of iron, iron is starting off with a +3 and it's gaining 3 electrons to get to a 0 oxidation state. So that's going to be reduced. Okay, so iron is going to be reduced and magnesium is going to be oxidized. So anytime that we see a single replacement reaction with where we're changing those charges, right, that's going to be a redox reaction. Okay, so most single replacement reactions are going to be redox reactions. Okay, and one of them is going to be oxidizing and one of them is going to be reduced. Okay, and the way I always remember it is Leo, loss of electrons, Leo, and Ger. Like when you're really cold, you say Ger. Okay, are you guys with me?
Yes.
Okay, good. Can I erase this now? Everybody's good? Everybody got it down? Okay. Nobody said anything, so I'm moving forward. Oops. Okay. So, an iron nail is dropped into a solution of hydrochloric acid. Okay. We want you guys to write the conventional equation. We want you to write the total ionic equation and then the net ionic equation. Any volunteers? Who's going to write on my screen, on my board? So let's start with the conventional. Any volunteers? Or do I have to volunteer somebody?
I would have, but I use a mouse, so it's really hard to write.
Come on, those are excuses. I can use a mouse. I can also use a trackpad. Now, if I can use a trackpad, mouse is
Well-
much easier than a trackpad.
Last time we worked with Alexis, he really helped me out. He can write, I'll talk.
Alexis, are you gonna write for her?
Yeah, I don't mind.
Okay.
What am I writing? The conventional?
Yep.
Mhm. It's
Isn't
So
it-
how about you do the conventional and then we'll have Brenda do the net ionic. Or the total ionic.
I'm on a mouse too, by the way.
Oh, he rubs it in.
Clearly.
Iron. That's right? Fe plus HCl.
Mhm.
You want me to write what it produces?
Hydrogen, gas.
Yeah,
H2.
just H2.
Okay, so normally under oxidation conditions, you're gonna end up with or single replacement reactions. For iron, you can end up with Fe2 plus, or you can end up with Fe3 plus. So let's go ahead and do it in the case of Fe3 plus. So iron 3.
So if that's the case, would you be, I mean, they will usually say what kind of F is, right?
Yeah, so usually I would give you what it is to start it out with, because you do have the possibility of both ones. It really just
Okay.
depends on how it's done. So
Okay.
I would give you that hint.
You said it's a 3 charge?
It's gonna be a 3 charge
All right.
here. Yep. But the initial, the iron nail isn't gonna be a 3 charge. That's gonna be a 0 charge, right?
Oh, that's right.
But I'm just telling you on the product side. In almost in every other case, it's gonna be a 2 plus charge. So like if you had cobalt, or if you had gold, or if you had, it's, with that change, you're gonna end up with a +2 charge in most cases.
So before we continue to the next part, we have to balance out the equation, correct?
That is correct.
So a 3 in front of HCl and a 3.
2, 3, actually a 3.
Are you sure?
I think it will be a 6. No, wait, hold on a second.
Yes, 6.
Did you get that, Alexis?
Yeah, she said a 6 in front of where? The CL?
HCl.
Oh, that's like
And it would be a 2 in front of the F. No,
Mm-hmm.
the product side, 2. 2, and then a 2 on the other F, 2. 2, 2, 3, 6.
And a 3 in front of H2.
Correct.
See what this group test has done to you guys. My gosh, you guys make me so proud. I'm gonna start bragging to everybody again.
By then, when it's that test due?
So your test is due at the end of the semester. So it's technically due not this Friday, but next Friday.
So that the hearing.
Mhm.
Aside from that, are we gonna have any days of makeup? Just because on the 9th, it's our last day is the 19th, right?
So
My brother's graduation at Sac State is Friday. That Friday.
are you serious? Do you want to take
Mhm.
it early? Do you want to take it on Thursday?
The last day?
Your exam, yeah, your final.
I believe that's the best thing I can do.
Okay, so you can take it on Thursday if you want to take it on Thursday. And again, it's an hour, right? And so you'll be able to get it in, get it out, you're good to go.
Okay.
Or just show up on Thursday. I'll be there.
Mm. At what time?
Class starts at 6, so can you make it at 6 p.m. Thursday?
I'll try to arrange something.
Okay. Yeah.
Okay.
Let me know if you can't, so I may be able to set something up so that somebody else could proctor the exam for you.
Okay, that's fine.
Anybody else who wants to take it on Thursday, you're more than welcome to take it early.
So for the total ionic equation,
What are we going to do for the total ionic equation?
isn't it just separating all of them?
Okay.
So we will have 2Fe.
Oh, so you expect me to be Alexis now?
No. I can't write. We're
2Fe.
selecting solid.
Okay. And
6H plus, right, class?
plus. Okay.
Mhm.
Good job. Keep going. Keep going.
Plus Cl. That's a gas. Is that an aqueous or is that a gas?
It's still going to be aqueous because it's going to be the ion, right? How many CLs?
6.
6.
Cls minus aqueous.
Okay.
Then it'll be H plus, no, 3H
No.
plus.
3 H2 gas.
3H2 gas. That's right, because we're not going to
Oh,
separate them.
Two
Right.
gas.
Good job.
It's still bright outside.
2 Fe3 plus.
Fe 3 plus.
Plus 6.
CO minus.
Yeah.
Good job. Hey, who are my spectators?
Cl minus.
Okay. Okay, Alexis, you're starting to get too good at this that your handwriting looks better than mine. So you may end up having to write for the whole class there.
Oh no.
So we have the net ionic equation. Okay, what's left?
2 Fe solid. Six hydrogen ions.
Okay,
3 H2 gas, the products. Plus 2 Fe ions. 3 plus, yeah.
Okay, now here's a hard question. Who's going to be oxidized and who's going to be reduced?
Fe is oxidized.
So Fe is going from a 0 to a +3. So that means it's losing electrons. So you're right, it's going to be oxidized. So that means that what's happening to the hydrogen?
Reduced,
It's going to
reduction.
be reduced. That's right. It's gaining electrons because it's going from a +1 to a 0. So it's gaining. Simple. Piece of cake. Piece
I
of
have a question.
sand. Yes.
Doctor, from the exam, from the
Okay.
practice exam,
Oh, you mean a take-home exam?
no, the practice one, the practice
Okay.
exam.
Yeah.
When you don't have it in solution, it's just the solids and gases and to another solid. How do you tell which one is being reduced or oxidized?
Good question. Okay. So you're saying in the case where you don't have ions,
Yes.
so typically if you're adding hydrogen to something, that's going to be reduction. And if you're adding oxygen to something, that's going to be oxidation.
Okay, the actual question in the practice exam is aluminum solid plus Br2 gas equals to aluminum
So you said
Br3 solid.
aluminum solid.
2Al solid
Okay.
plus 3Br2 gas gives aluminum AlBr3 solid.
Okay.
2AlBr3 solid.
Okay. So this forms an ionic compound, right?
There's a 2 in front of AlBr3.
Okay. So
Okay.
this forms an ionic compound, right? Okay. So if it forms an ionic compound, what's going to be the charge on the Al?
Three?
It's going to be a +3 charge, right?
Yeah.
Okay. So if you're going from a 0 to a +3, then what is that going to be, oxidation, or is that going to be reduction?
Oxidation.
Oxidation. So in this case, aluminum is being oxidized, right? And then the bromine is being reduced, right? Because it's going from a 0 to a -1. So that means it's gaining electrons.
So it doesn't matter that the product is solid?
Yeah, it doesn't matter that the product is solid.
Okay.
And that shouldn't have been a minus here. So. Okay. Any other questions? That's actually a good question. No other questions? Good. Okay, let's see if we can get some more stuff done. Okay.
Dr. Hayes, for the final, are we using the same study guide that you gave us?
Yeah. The multiple choice test?
Yes.
Yes. Yeah, that's your practice finding.
Okay.
Yeah.
Is it, do you know how many, is it the same amount of questions?
No. No, on your final, there is I used to know it off the top of my head. I think there's 55 questions and you have 60 minutes to answer them. Or it's 50 questions in 60 minutes.
Just because I want to prepare.
60?
Yeah, just 60 minutes. Yeah. It'll go fast.
Including the calculations?
Yeah, a lot of the questions are going to be big picture questions. You're going to look at an image, you're going to say, well, is it a mixture? Is it a solution? Is it a mixture? Is it a homogeneous solution? Is it a gas? Is it a solid? There are going to be questions like that, big picture. And there are going to be other
Okay.
questions where there are going to be calculations. So you're going
Are
to
you-
get, it's on average about a minute per question.
Are we gonna get the same similar questions to the ones of test 3?
No, they're not going to be to that level. No.
To that extreme, you're gonna
No.
say?
So they're going to be really simple compared to test 3. You're going to kind of
Okay.
chuckle when you see it. Yeah.
Similar to the practice exam?
It's going to be very similar to the practice final. Yes.
Okay.
Very similar to the practice final.
Okay,
Okay. They're not going to be the same questions, but it's going to be similar.
okay.
Okay.
As long as it's not like similar to number 3, then.
No, not exam number 3. No. Yeah. And it's all multiple guess.
Okay.
Okay. I mean, multiple choice.
Multiple guess. That's funny.
Okay. So
Smart
if we have a-
guessing.
Yeah. If we have a reaction between zinc and a solution of copper 2 nitrate. So can you guys write the conventional equation for this and the total ionic equation? Okay. And then the net ionic equation. Who's going to be my volunteer this time? I think Alexis should do it this time, right? Since he wrote for everybody else. Thank you for volunteering, Alexis. Or did you leave? No, he's still there. Alexis?
Yeah. Sorry.
Are you volunteering? Thank you.
No.
You said yeah.
To do what?
To do this problem.
I'll be honest with you. I've been in and out of
Okay.
this.
Well, read the problem, and
okay.
then you can do it.
A reaction occurs when a piece of zinc is dipped into a solution of copper 2 nitrate. Write the conventional total ionic and the net ionic equations. Let me pull up my P table here. Zinc has a +2 charge, or is it +1?
It's going to be a +2 charge.
+2. Okay, so that's your metal, right?
Mm-hmm.
And copper 2. So that's Cu. And then nitrate is it? This is just, I don't have my sheet on me. Is it NO3 and it's a minus charge?
Yes. Yes.
Yeah. So you need 2 of these.
Okay.
And then this is your AQ. So this is a single displacement,
Okay.
right? So technically you would have to look at the metal activity series to
Okay.
see if these 2 react. I'm assuming that you wouldn't put 2 things that don't react
Okay.
for this thing. So AQ. And so being that this is a 2 charge. Oh, I messed up. Sorry. So being that the copper, the zinc is a 2 charge, this would also be a 2, and then the copper would be alone as a solid.
Okay.
So the change that occurred here was the zinc came into the AQ solution. And then the copper went from an AQ to a solid and a precipitate.
Okay.
And for balancing, it is balanced. Unless the 2
Yes.
goes over here, it does not, right?
Nope.
Okay, so therefore it's balanced.
Yep.
All right, I'm done.
No, you're not. That's just the conventional.
I don't know how to do the other one. The total ionic. Well, I mean, okay, so it would be Zn, and then you said it's a 2 plus.
No, because it's a metal, so you.
It's solid.
Oh, that's right. It
That's
doesn't need the charge.
That's right.
Okay. Then you have your Cu. This
Okay.
is aqueous, so this does have the 2 plus.
That's right. It's gonna split up.
Yeah. Okay. And that's AQ right here.
Mhm.
And then the NO3. Oh, there's 2 of them.
That's right.
Yeah. 2 NO3s. And that's aqueous. And that is a -1.
Okay.
Right? Or 1 minus. I don't know if would this be wrong? I sometimes put the minus first.
It's just minus actually. In this
Oh, it's
case.
just minus. Okay.
And it would make me feel better if you write that O a little bit bigger because it's really, it's pressing me right now.
I'm just kidding.
Smart ass.
All right. My hand slipped on the mouse. That's why.
Yeah, I know. I do it all the time.
All right. So you got your NO3. It's a minus charge that accounts for both of them, and then here is where the 2 plus charge takes effect because it's an AQ.
That's right.
Okay. And then this changes to AQ. And then you have your 2 NO3s in AQ. This is a minus. And then finally, you have your CU, which is a solid. And it does not, oh, man, sorry. It does not have a charge because it's a solid and it's alone.
That's right.
Okay. I don't know what's going on here. Sorry. Okay. Now for the net ionic equation, I am gonna need help. I don't know where to start.
Okay. What are your spectators? Let's get rid of our spectators.
So okay.
It was exactly the
Spectators.
same on both sides.
Yeah. It would be right here. Right?
Okay. So get rid of them. That's all you need to do.
Oh, okay. Can I just do this? Just kidding.
Lazy bum.
Oh man. Okay. So nothing else changes, right? Because these all change state.
That's right.
And that's the only difference. Okay, so I guess I'll do it in red. And the handwriting is getting worse.
Too many cocktails.
Yeah, that's what it is, huh? So from here, you would just go straight like this?
That's right.
Okay. That's the CU, right? All right.
Okay, that's it.
I've been bullied enough. Thanks.
Anytime. Okay, so now it's important that you guys understand. So when you get the total net ionic equation, right? Total net ionic equation has everything in it. I'm sorry. The total ionic equation has everything in it, including the ions that aren't doing anything. Now, the net ionic equation only has the stuff that's doing stuff in it, okay? And that's the key.
Reactions, okay.
That's right.
And that was the difference in number 8, right, for the test?
Yep.
Like, people were
the different parts, right? And so, because if you think about it, because all of those ions are still there, right? So they have the possibility of interacting as soon as you add something that they can actually interact with. But the key is to get something that they interact with, right?
Right.
And that's the secret. Secret
Gotcha.
sauce there. Okay. So here is the activity series, right? Now, the way the activity series works is that there's a hierarchy, okay? There is a hierarchy in chemistry, okay? So if we have all of the ones that are over here, if they're above something else below it, right? They're able to replace, that metal is able to replace one that is below it, okay? If it's in a chemical compound, okay? So let me give you an example. So if I have lithium metal, and let's say we had magnesium chloride solution. Okay, now since lithium, that metal, is greater than, higher than the magnesium, it's able to replace the magnesium. And we would get a reaction where we have lithium chloride and the metal, magnesium metal, would precipitate out. Balance it out. Okay, so we would get a reaction. Now let's say we had the opposite. Let's say we had magnesium metal. And we had lithium chloride solution. Okay, this would give us no reaction. Often you'll just see it as written as NR. Okay, and that's because magnesium metal is below the lithium. And so it can't replace anything that the lithium is in. Okay, so the way I like thinking of it is that the person on top is a rich person. And that individual person could come in and take over my entire life because I'm poorer than they are. So they can come in, they can take over my car, they can take over my house, they can take over, my girlfriend who likes money, So they're able to sit there and take my place completely, where a poor guy can't come in and take that rich guy's house, that rich guy's car, or that rich guy's girlfriend if she likes money. Does that make sense?
Yeah.
Okay, do you guys mind if we take a 5-minute bathroom break? Because I need to go to the bathroom. Actually, let's make it, you mind it's 10 minutes? I'll be right back. 4.5 minutes, okay.
With sig figs.
With sig figs. Are you guys ready? Okay, so do you guys understand the activity series? Okay, good. Okay, so let's move forward. We're almost done with this chapter. Pretty excited. Okay, so sometimes, so we've talked about oxidation already. So sometimes when we talk about the oxidation, we talk about the oxidation of organic compounds. But that's basically when things that become oxidized is basically when we're adding oxygen to things, okay? So here, these are going to be products of oxidation. So when we have a combustible reaction, that's going to be an example of oxidation. So in this case, our carbons are going to be oxidized, and then the water actually is going to be reduced. Okay. So you guys already know how to write a chemical equation for a combustible reaction. You guys have done this many times. So in this case, we have ethane. We know that oxygen is going to be required. So what are going to be my products? You've been doing this since the very beginning of class. Edgar,
CO2 and water.
okay. Okay, is it balanced? Edgar, is it balanced? Ah. Yes, it is balanced. No, maybe.
No.
No. Okay, so what do I need to do to balance it? How many carbons we have on our reactant side?
2,
How many hydrogens?
6,
How many oxygens?
2,
On the other side, on the product side,
1,
hydrogens,
2,
oxygens.
3.
Okay, so it's clearly not balanced. So what do I need to do to balance it?
Two on the carbon.
What was that?
2 on the carbon. We start with 2 on the
2.
carbon.
Okay.
So oxygen.
So then that gives me a total of 5
5
oxygens, right?
Yeah.
Okay. And then what about the hydrogen?
We can put a 3. I don't think it will be balanced.
No, it doesn't look like it's going to be balanced, but we're going to end up with a total of 7 oxygens.
Mm-hmm.
But we know that since we have an uneven number there, what are we going to do?
3.5 in oxygen.
Okay.
Then we multiply by 2, everything by 2.
Okay, so we multiply everything by 2. And
Mm-hmm.
then put 7 here since it's 3.5.
7,
And then
6. 4.
and then okay.
Yes.
Okay, piece of cake, not too bad. You're like, man, that's just so easy. We used to do that all the time, right? Okay. So when we talk about double replacement reactions, right? So often we're going to get a precipitant. The way that we determine if there's a precipitant is by using tables. Okay, so I'm going to show you guys how to do that table. Okay, so you guys have this on your polyatomic, on your periodic table packet? Everybody has this?
Yes.
Okay.
I do. I don't know about the rest.
Okay, you do. That's all that matters. Everybody else is just timed out already. Stephanie, you got it. I know you do, right? Good. Okay. So if we have this table, right, we can just go across to figure out whether or not things are going to be soluble. If it's in green, it's soluble, basically means it's going to be dissolvable in water. It's going to be aqueous. Okay, if it's red or that pinkish color, then we know that it's going to be a precipitant, right? It's going to be a solid that isn't dissolvable in water. Okay, so the way that we would do this is, let's say we had let's say we had cobalt nitrate. Cobalt nitrate. And it's going to be reacting with ammonium carbonate. Okay, so if we go down here to cobalt, go down here to cobalt, and we go over to nitrate, we'll see that that's soluble. So that's going to be aqueous. If we go over here to the other side, we have ammonium carbonate. It's also soluble. So again, that's going to be aqueous. So we know that this is going to be a double replacement reaction. So we know that's the swingers party. So who hooks up with who?
Cobalt carbonate?
Okay, so we're going to get cobalt carbonate,
Yeah.
cobalt 2 carbonate.
Mhm.
Okay, so now we were going to go down to cobalt 2 carbonate. We're going to bring, okay, so that's nearly insoluble. So that basically means it's going to form a precipitant. Okay, so we're going to put a solid by it. And then the other,
Ammonium nitrate?
okay, ammonium nitrate. So if we go across to ammonium nitrate, is that going to be aqueous or is it going to be a solid?
Soluble.
Okay, so that means
Yes.
soluble means S.
No, aqueous.
Aqueous, that's right. Okay. Okay, is it balanced?
No.
What do I need to do to balance it?
Two on the ammonium nitrate, sorry.
Okay. Questions? Concerns? Cash? Okay. So how are you guys feeling about that? Not too bad? Okay, perfect. So we'll see, we'll let you guys do one. So let's say we have, we'll go iron chloride, iron 2 chloride. So and barium hydroxide. Okay. Okay, so the iron 2 chloride, is that going to be soluble? Or is it going to be insoluble? Or is it going to be aqueous or?
Soluble.
Okay, so that means, that's right. So that means we're going to put right next to it what?
Aqueous.
Okay. So we're going to put that AQ. And then what about the barium hydroxide? AQ. Okay, what are going to be my products?
Dr. Henry, I have a question.
Yep.
In double displacement, the reactivity series doesn't matter?
Nope.
Oh, okay. Then we'll have FeOH2 and BaCl2.
Okay. Stephanie, do you agree with her?
The iron hydroxide is solid.
Okay. And what about the barium chloride?
Aqueous?
Is it balanced?
Yes.
Everybody agree? Okay, so let's move forward. So this is just another extension of that table. And this is just the hardcore rules of solubility, right? So we have that table that makes it a lot easier, or we could sit there and try to learn all of the different rules, right? So often you guys can use the table, but if it comes to it, you can use these rules, okay? Are you guys clear?
Yes, sir.
Okay, good. Okay, so
Not Alex.
what was that?
Said don't pick Alex on this one.
Are you sure? Okay, it says a solution of lead-2 nitrate and sodium bromide are combined. Write the net ionic equation for any precipitation reaction that may occur. Okay, so what are the chemical formulas? Okay, Stephanie, you gonna help me out? Chemical formula for lead-2 nitrate? Okay, that's right. So Stephanie says PB parentheses NO3, and there's two of them, plus, what about sodium bromide? Okay, NaBr, that's correct. So are they going to be the lead-2 nitrate? Is that going to be soluble or aqueous, or is it going to be a solid? Aqueous. And what about the sodium bromide? Aqueous, that's correct. Okay, so it's a double displacement reaction. So who's hooking up with whom? Okay, so we have lead bromide. That's correct. Is that gonna be a solid, liquid, gas, or aqueous? Solid, that's correct. And we have sodium nitrate. Solid, liquid, gas, or aqueous? Aqueous, that's correct. Is it balanced? Okay, what do I need to do to balance it? Where am I putting which coefficients? We get a 2 here. And a 2 here. That's correct. Okay, so all the ones that are aqueous, they're going to do what? Mitzi, what are they going to do? Okay, somebody want to help Mitzi out? Alex.
He's not here right now. What's the question?
I said, what are all the ones that are aqueous going to do?
They're gonna
Or
be
they're
the
not
spec
ionic.
or wait, whoa.
They're going to separate. That's right. They're going to separate. Thank you, Brenda.
Thanks, Brenda.
Brenda, I don't know which one to call Brenda 1, Brenda 2. So the other Brenda that wasn't talking. Yeah. So we know that we're going to end up with lead 2, aqueous. And then how many nitrates are we going to end up with?
Those.
2.
Okay. That's correct. How many sodiums? Ions?
2.
2. How many bromium ions?
2.
2. All right, bromide ions. Okay, what about on the other side, on the product side? What's going to happen to that lead 2 bromide?
Stays the same.
It's going to stay the same. That's correct. Okay, and then the sodium nitrate.
Will separate.
Okay. Who's the spectators?
Sodium and
Sodium
nitrate.
ion?
Yeah,
Okay.
and nitrate ion.
Hey, when I run out of room. We said sodium and our nitrates. Okay, so now all we have to do is write what's left over for the net ionic equation. And we're good to go. Okay, questions? Concerns? Cash?
Yeah.
Wow.
So this whole thing that we're doing, what is it called in its entirety?
It's typically called ionic equations.
Ionic equations. Okay.
Yeah. And so, it really just shows you what's really happening when we have ions in solution, right? Because they're going to separate and then they're going to come together if they can come together.
Got it. Okay.
Okay. Okay. Good. Okay, so let's see. So this is going to be similar to what we see with the neutralization reactions, right? So you get the formation of water, so that which is liquid. And so, and sometimes you'll get molecular products that'll be formed from it as well. So when those happen, you know that they're not going to, okay? Let's see. So I'm not going to do this question. I'll let you guys do that one on your own or look over it. It shouldn't be too hard, right? I guess, yeah, shouldn't be too bad. Although we're missing a whole word. It should have been sodium hydroxide instead of just sodium. Okay, now sometimes when we have double displacement reactions, sometimes the products that we end up with will end up being unstable, okay? So these are some examples of that. So if we get hydrogen combining with carbonate, it's gonna form carbonic acid. Carbonic acid isn't gonna be stable. It isn't gonna last long. It's gonna end up breaking down to carbon dioxide and water. That's the same thing with if we have the hydronium ion and sulfite, we're going to get the formation of sulfurous acid. And then that's going to break down to SO2 and water. And then that's the same thing that happens with ammonium and hydroxide. It's going to form ammonium hydroxide. And then that's just going to break down to ammonia and water.
Isn't
Okay.
SO2 and H2O acidic rain?
Yes. So when they come together, they're going to form sulfurous, right?
Yeah.
And sulfurous acid is actually unstable. So it actually will break down to sulfur dioxide.
Okay. And you said carbonic. Is that what you said? Acid?
Yes.
Um,
Carbonic
is
acid.
is that the conjugate base? Or so like when
Carbonate would be the conjugate base.
conjugate. So whatever your base is, that becomes your conjugate base in the product side?
No. So if we have an acid, right? So
Yeah.
typically the way it works is one thing becomes your acid and one thing becomes your base. So let's say, for instance, we had hydrochloric acid, right? Let's see. Okay, so here, hydrochloric acid is going to be our acid, right? This is going to be our acid. And let's assume that we just use water. Water is going to be acting as our base.
So, okay, so HCl is giving the proton and water is
right.
accepting it.
That's right.
Okay.
Okay.
Usually water's the best base, right? On Earth?
No, it's not necessarily the best based on Earth. It's just able to accept things, right? Waters is very accepting.
That's what I meant. Sorry, no, not the best, but
yeah, it's cool with accepting. Yeah. So in this case, we end up with the hydronium ion, right? Which is basically how we define an acid, right? That H plus, and we end up with Cl minus. Okay, so here. This is going to be our conjugate acid.
Okay.
and then Cl is going to be our conjugate base.
Do you have to, in the product side, put the plus and the minus? Or
Yes, you have to put the plus or minus because otherwise it's wrong because you're forming the ions in this case, right? If you don't put
Okay.
that plus and minus, then it's incorrect. Does that make sense?
yes.
Because in this case, you're getting total dissociation. Those ions are splitting up. And so they have to be shown to be ions. Okay, so this guy would be the conjugate base in this case. Okay. Where over here, the hydrochloric acid is acting as our acid. And then here, water is acting as our base.
So in this case, it's not dilution of acid?
It is a dilution of the acid, essentially,
Mhm.
right? We're just helping it dissociate a little bit better, right? But what's happening is that water is acting as a base, and that's allowing the H plus to attach to it. Remember when I told you that H plus like to attach to stuff?
Mhm.
That's the case right here. Okay.
Okay.
So if you think about this, this is exactly what's happening in this situation here too, right? Because in the case of the ammonium ion, right? The ammonium ion is acting as an acid. The hydroxide is acting as a base. Usually hydroxide acts as base, right? So what really happens is that the H is going over to the OH to form water. And then we just end up with NH3 and water. Do you guys see that?
Yes.
Cool. Okay. Okay. I'm also going to let you guys do this one on your own. Pay attention to the byproducts. Well, it doesn't matter. I already showed you the byproducts. So, okay. Okay, and we've already talked about what happens when everything is aqueous. If both of your products are aqueous and things don't come together, this is a good example here. So here, oh, this one isn't a good example. Let me get nothing. Hold on. Okay, so if we have sodium chloride and potassium nitrate. Okay, so in this case, if we separate both sodium chloride into their ionic forms, we have sodium ion, we have chloride ion, we have potassium ion, we have nitrate ion, right? The problem is that nothing forms a precipitant. Since nothing forms a precipitant on the other side, you still have these ions present, right? And so there's not going to be a reaction. So you're not going to see a reaction. So this would be an example of no reaction because everything is going to cancel out as a spectator. Can you guys see that?
Yes.
Okay. And so if you guys think about question number 8 on your take-home exam, this is a good example for that. Right, Alex?
Yeah.
He's just saying, yeah, he wasn't paying attention.
I'm finalizing my report.
Oh,
And
okay.
I was updating what you said about the plus and minus.
Yeah.
Because I had acid base.
Okay. 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 So, any questions? Concerns? Cash? Chocolate cake with strawberry frosting? Or strawberry cake with chocolate frosting? I think that's better. Yes, there's a question. The cookies were delicious. Brenda, did you have a question?
Me?
No, the other Brenda.
Oh.
Let's see, hold on. Are there any other questions? No other questions? Anybody want to give me $3 million so we can call it a day? You don't have to worry about the final then. We're going to the Bahamas. Actually, I'm going to the Bahamas. I don't know about you guys. Okay, so I will see you guys for presentations tomorrow. Okay, you guys have a good night.